Alright, everyone, it's a Sunday morning about 7 a.m. That's the most magnificent morning sky. I'm drinking coffee, and for some reason, I'm not done explaining, in particular, not to myself. This seemed like a brilliant time to look into this open source screen recording software, OBS. You see, when we usually run normal lectures, I get to bring a lot of stuff to explain the physical meaning of vibrations, and we can't really do that. But what we can do is to try to do some virtual testing using MATLAB. Right, so here I have opened the Kraken, and these are my models I have here. And the very first oscillating system I tricked you into analyzing even before we talked about vibrations was the pendulum, the mathematical pendulum or particle pendulum. So if I now try to run this, then I get this little animation of my pendulum moving back and forth, right? Swinging or rotating motion only driven by gravity. And if we wait just a second, we get the vibration responses. Yes. Here we have the frequency content of our vibration response, which is what we get if we do an FFT. If I just zoom in, for some reason on this laptop, the zoom function has been hidden pretty well, right? I see a peak here, right, which is the natural frequency of the system. If I plot my pendulum angle, right, I get this response. We recognize this as a harmonic function. There's no damping in the system, right? It just goes on, meaning that the amplitudes will remain constant throughout eternity, violating multiple laws of thermodynamics, but however, for many applications, being a pretty useful model. Now, if I move on to the vibration code I gave you in the lecture notes here, where I just numerically integrate the dynamic equilibrium of a simple mass spring damper system, then I could do a little bit of graphics at the end, not particular high level. But if we now define a mass, a stiffness, and a damping, and have no excitation force and no initial conditions, right? We should just get the static equilibrium, and nothing should be moving, right? That's the case. But this, we can tell here on the vibration position response, the displacement, that nothing is moving at all. But this is the system we'll be looking into now, right? We have a spring, a damper, and a mass. And we can just look into what the circular frequency is. It's 14.14 radians per second. My critical damping is 141 kilogram per second. So, if I now eliminate the damping from the system, I am dealing with a system which is, right, I have no forced excitation here, so I'm dealing with free vibrations. The case is undamped. How can I initiate a motion? I can either displace my mass away from the equilibrium, right? That would basically produce a spring force that would initiate a motion, or I can provide my mass with an initial velocity. If I start out by displacing the mass 0.1 meter, corresponding to pulling the mass 0.1 meter downwards, and look into which vibrations I will get, then we have the response here, right? You can tell I've pulled the mass downwards, released it, And the system is now vibrating freely with a circular frequency of omega n and a natural frequency Fn equal to omega n by 2 pi, right? So this is basically the simplest case of vibration. I can observe here that the amplitudes remain constant, right? There's no decay, there's no damping, no physical effects dissipating energy from the system. So these just remain constant. And the system just moves on and on and on. And I've set the time limit to 5 seconds, so we are just about done. We can tell we still have a harmonic response over here. The frequency is omega n. Now, that was simple and fun. If I now go back here, I could also initiate a motion by giving my mass an initial velocity. I could, for example, do that by hitting it with a hammer, right? That's a sort of very valid method of inducing vibrations. Hit systems with a hammer. So I will now give my system an initial velocity of 1 meter per second downwards. Now we can tell in the vibration response over here that the response starts at 0, right? But I have the same behavior as before. The motion has the oscillating motion has a frequency, a circular frequency of omega n, a natural frequency of Fn. So that is pretty straightforward here. Now, what would happen? This is not particular physical, right? There's no system where the amplitudes would remain constant. Energy would always be dissipated. So, in order to improve this model, I could add a bit of damping. I will start out with, that went wrong. I will start out with 2 kilograms per second of viscous damping. Which response will we now get? Let's have a go at that. We still initiate the motion with an initial velocity of 1 meter per second downwards. This is what happens. If you look at the response here to the right, what you can tell is that the amplitudes slowly become smaller and smaller, right? There's a decay rate now. Energy is being dissipated. And what we can tell just looking at the system is that this is lightly damped. It's very lightly damped, meaning that the damping applied is well below the critical damping. But we can still see here the response is decaying now. So, we'll be done in a second once we've reached 5 seconds of simulation time. Now, that was an example of a lightly damped system, but what if I would add a damping now above the critical limit? What was the critical damping again? It's 141 kilograms per second. Okay, let's go for 150, shall we? And have a look at what free vibrations in a heavily damped system look like. We can tell here, right? We initiate the motion with a downwards velocity of 1 meter per second, but the system never makes it through an entire vibration cycle. The oscillations are damped out before we make it through a cycle. So for heavily damped systems, there are no free oscillations. Right? That's the practical application of heavy damping. And I keep getting these messages when I kill the simulation before time, right? But that was the examples of free vibrations. Very useful. These come at a frequency of omega n, right? In the differential equations, the circular frequency, a natural frequency of Fn. Now, if I, for the very first time, now things get really interesting, at a harmonic force excitation. This is going to be fun. I go for a force amplitude of 10 Newton and a circular frequency of the force excitation of 10 radians per second. Now let's just initiate the motion only with the force excitation, right? So the system is at rest in neutral position when we apply this. Let's try to have a look at what that would produce. Now we have a force coming along here, and we can tell what happens over here, right? A motion is initiated, and what can we say about that motion? It's not particular regular, right? It's an irregular vibration response, since we are now, in a mathematical sense, dealing with the non-homogeneous differential equation. We all remember that the solution to those is the sum of a complementary and a particular term, right? One corresponds to the forced response, the other one to the free vibrations, right? So when we initiate a motion with a harmonic excitation force, we will trigger both forced and free vibrations. Now, if the system is undamped, the free vibrations will be present for all eternity, right? Meaning that our response will be irregular, look weird. But if I now add a bit of damping to my system, let's say 10 kilogram per second, and still initiate a motion with a harmonic force excitation, let's have a look at what happens here. Right. Initially over here we can tell that the motion is still weird. It's still irregular. But let's see what happens in time, shall we? Oh, this is interesting. What is going to happen here is that we initially still have both free and forced vibrations present, right? For the first few cycles, this is what we call transient vibrations, but as damping make the free vibration vanish, right? As these are dissipated due to damping, we can tell that the response become regular, right? This looks like a beautiful harmonic curve. This is what we call the steady state response, which we will encounter in all real life systems, since there are no systems without damping, right? So when you turn off a machine, turn on a machine, initially you might have an irregular response, but you will reach this phase here called the steady state, where we only have the forced vibration response remaining, and the period or frequency of this response in the differential equations is now omega f, right? The circular frequency of the forced excitation response. That is now the frequency of the motion here, right? The mass will have to oscillate at the same frequency as the forced excitation is applied with. So that was fun. What kind of damage can we do now? If I now look, what was my natural frequency of the system again? It's 14.1421. What would now happen in an undamped system if I would add a forced excitation with a frequency, a circular frequency, equal to the natural frequency of the system? Right. What is going to happen now? You can start guessing, right? It's not that hard to guess. What we can tell now is that in the undamped system, if the excitation frequency equals the natural frequency of the system, then amplitudes become larger and larger. And in principle, if there is no damping in the system, these will, theoretically speaking, become infinitely large. This is what we call resonance. This is what we call resonance, and it is a phenomenon we try to avoid in mechanical design, since this, for obvious reasons in machinery, would lead to catastrophic failure. So we don't want our forced excitation to have the same frequency as the system naturally would oscillate with. However, we've talked about that just a second ago, there is no such thing as an undamped system. So in most systems, sorry about that. So in real life systems, the amplitudes wouldn't become infinitely large. These would reach a finite size in some steady state. Right. Again, the frequency of the forced response is governed by the excitation frequency. What we can tell now is that the amplitudes do not keep growing. Right? The magnitude of the amplitudes stabilize now. I'm still driving the system with this critical frequency, but these don't become infinitely large because damping sets a limit to how large these will become. That's also what would happen in real life machinery, right? There is no such thing as an infinite vibration amplitude. What we can observe here is, however, that my motion and my forced excitation are in phase, meaning that when my mass is in maximum downward position, I also have a force acting downwards, right? When my mass is in maximum upward position, my force is acting upwards. Forced excitation and vibration response, the motion, are in phase. If I now add a frequency of the forced excitation above the natural frequency, let's go for 20, then here's what happens. Right. We'll see that after a short while, displacement and force are no longer in phase, meaning that when my mass is in maximum downward position, I have a force acting upwards. Right. So you could interpret this as the mass no longer being capable of keeping up with the forced excitation. It falls behind the displacement of the mass. This happens if you add vibration, if you add forced excitations with larger frequencies than the natural frequency of the system. If omega f is larger than omega n, then the vibration response and the excitation force will no longer be in phase. This is what you can observe here. So that was just a bit of virtual testing with MATLAB. You can have so much fun with that program. Also, what I could do here is briefly to go back to my Kraken, do the same system, right, which is contained in this model file here. Now I have numped my pendulum above and we will run this file. I can do the same system, but now I add an excitation force as a chirp signal, right? Meaning that the excitation frequency no longer is constant, it increases. So let's have a look at what is going to happen if I add an increasing frequency in the excitation, which is the simplest thing we could do to simulate our run-up. This is what happens when we are starting a machine, because a machine does not start at a constant speed, right? The speed increases over time. Now you can see that my mass, then basically the oscillations, the amplitudes become larger, and now they decrease again. So what happened was that we ran the forced excitation through the range of the natural frequency. Now the forced excitation happens at a larger frequency and we can tell the amplitudes are small again. If I look at the frequency content of my vibration response here to the right and my displacement of the mass, I get these two curves here. This is the natural frequency of the system. Over here I can tell basically what happened. I added a forced excitation. This leads to this displacement. This happens at an increasing frequency, leading the amplitudes to become large as we pass the natural frequency. This is the range where omega n is equal to omega f, right? The forced excitation happens at the same frequency as the natural frequency, then the amplitudes decrease again and become small. So that is the most simple run-up simulation we can do. I could of course also do this with two masses, simulate the same thing. As far as I recall, this takes a bit longer to run, right? The Kraken isn't a program that's particularly efficient. It's actually quite slow. Right, here we go. It wasn't that bad. So I have now two masses connected with springs and a force excitation applied with a frequency that increases. Right. Now we can already start to see the first mode. I have 2 degrees of freedom, meaning the system will have 2 eigenfrequencies and 2 corresponding mode shapes. Now this is the first mode we just saw, right? The masses are oscillating upwards and downwards along with each other. They move together. What happens briefly afterwards, as the frequency of the forced excitation continues to increase, is that we see the second mode here, where the masses no longer move together but towards and away from each other. An accordion mode, you could possibly say. It's very clear here now. And amplitudes are large. What happens as the force frequency increases? The amplitudes become smaller again. I must add that actually this is a spring and damper element in the Kraken. There is a damping in the system. I just never bothered actually plotting a damper, but there is a damping. But this is what our run-up would look like in a system with 2 masses, 2 degrees of freedom, corresponding to 2 natural frequencies, each with a mode shape. Here we saw both mode shapes being triggered by a forced excitation. We just have to leave the system here, leave this little animation running, because in a second, when this is done, we'll be able to see the displacements and the frequency content of the vibration response. Come on. Yes. Here we go. This is for the first two curves here are for the lower mass, number 2. We can tell I have 2 peaks now, the first and second eigenfrequency. We can also tell that I, during run-up, passed the first and the second eigenfrequency. These should be even clearer on the upper mass, since that's where I'm adding the forced excitation. Yes, here we go. Right, I have a peak here and here. This corresponds to that we pass the first and the second natural frequency. Right. So that, I hope that sort of actually explains a little bit what the physics about behind all these fine differential equations are. Right. If you actually look into this for a longer time, it's almost scary how well the physics of the system fits the theory, which is not particularly surprising because this kind of mathematics is developed to solve these particular problems, right?